Hello again, and thank you for joining us today as we discuss the recent changes to the ANSI B11.19 standard and the different solutions for whole body access. My name is Lisa Shaw, and I'll be your moderator. I work on the marketing team at SICK, and I'm excited to be hosting today's session. During the webinar, the second of a four-part series, you will learn how to apply risk reduction measures for whole body access, methods for preventing undetected presence of individuals, combining risk reduction measures, and so much more. Just a little housekeeping before we get started. I want to share that a recording of this webinar will be emailed to you following today's session. Also, feel free to ask questions at any time during the webinar by typing your questions into the Q&A section on the right-hand side of your screen. We'll take some time at the end of today's presentation to address as many questions as time allows. Now I want to turn our time over to today's presenters, Chris Serrano from SICK and Kenji Furukawa from BridgeStone Americas. Chris is a safety standards and competence manager at SICK. He is a certified functional safety expert and is a member of numerous ANSI committees and international standard working groups. Kenji is a senior technology specialist of safety design at Bridgewater Americas. He has 21 years of experience in control design, software development, risk management, and validation standardization. Chris and Kenji, please take it away.
Thank you, Lisa, and welcome everyone today. As Lisa explained, this is part of a series of webinars that SICK's been developing is to go along with the new release of a brand new revision to an important standard in the US market, which is ANSI B11.19. And today's session is going to be focused entirely on the concept of whole body access. We have a lot of material to get through, partly because there's a lot of new and exciting content in the standard that I'm really excited about and glad to be able to share with you today. So we'll start with understanding or explaining what whole body access is. We might think we understand it, but just to get a clear definition of it, let's look at how it's described in the standard. In the standard, whole body access is a situation where an individual can be completely inside the risk reduction measures. So essentially there's a hazard, it's inside some area defined by a perimeter or safeguarded space. Ideally, the solution is designed so that when we access that area, the hazard comes to a stop. But the real situation that whole body access addresses is how do we prevent it from starting up again when people are inside this area? Could be a large area, could be a moderate to small area, but nonetheless, if somebody could be inside, they're completely in the area where the hazard could potentially occur, what do we do to prevent it? So that's whole body access. It's gone by a number of different names in the past. In the standardization world, we're trying to harmonize on one so that we're all talking about the same thing, but you might know it by other names, but essentially this is the scenario that we're addressing. To better understand it, we also have to look at a couple other definitions. One is perimeter. What is a perimeter? We think we understand it. To be clear, it's the boundary or around an area created with risk reduction measures. That's how it's used in this context. So if we have two different machines, both with hazards, machine A, machine B, and there's some safeguarding solution around it, in this example, both of them have perimeters. However, they do not both have whole body access. In example A on the left, there's no ability for the person to be completely inside the risk reduction measures, the red perimeter, whereas on the right with option B, if they can be in that area, then it is whole body access. We also have to understand the perimeters can be established using either engineering controls. So this is where we're talking about physical barrier guards or safety devices as defined in the standard that are integrated into the control system. Or a perimeter can be defined with awareness barriers. In the risk reduction hierarchy, these are considered lower order measures because they only provide a tactile awareness of a hazard, but don't actually prevent someone from climbing over or through into the hazard zone. So both of these are perimeters. And which one we select for any risk application is going to be based on the level of inherent risk, which means that risk assessment helps us determine where and when to apply what type of measures. Some people might have a very high risk tolerance, some might have a very low risk tolerance, but nonetheless, the risk assessment is going to help determine what type of measures are applied. So this is a funny example, but an example nonetheless, where the middle shows us engineered controls, guards, preventing access to hazards, whereas on the sides, there are examples of awareness barriers. If the hazard inside is large enough, high enough, we probably want to lean towards using engineered controls to prevent or control access to the hazards or contain the hazards to prevent them from getting to the exposed individuals. So understanding the perimeters could be either with engineered controls or awareness barriers. We also need to consider this other term used in the definition, which is a safeguarded space. Safeguarded space is an area or a volume around a hazard specifically defined with engineering controls. So when we define a perimeter with engineering controls, that's a safeguarded space. If we define a perimeter with awareness barriers, that is not a safeguarded space. So understand that whole body access applies in both conditions, but there is a slight deviation between them, and that safeguarded spaces are a subset of perimeters. So examples where whole body access occur, there's a couple examples here on the screen. All of these have defined perimeters. The two on the left are safeguarded spaces because they're using engineered controls. In the first option, there's a vertical light curtain that defines the perimeter. In the second option, there's a fixed and interlock guard dividing the perimeter, so that's the safeguarded space. And in the third example, we have an awareness barrier being used to define the perimeter. And since you can get through over, it is not a safeguarded space, but it is a perimeter. And then clearly we have another delineation here that whole body access doesn't only occur in large zones or applications like robot cells and processing equipment. It could also occur at the point of operation when the safety distance is such that it's the device to be mounted correctly is so far away that somebody could stand between the device, the perimeter, and the hazard. So these are all different takes on this concept of whole body access. So to better define it, there's really two conditions that have to exist. You have to have physical access to the space, and you have to have adequate room inside the space. So if we're talking about human exposure, this is an exaggeration, obviously, but there's not enough space in the door for a person to get inside, nor is there enough space inside for a person to be, so that does not qualify as whole body access. If we do have enough space beyond the perimeter, but simply cannot get into it, that also does not constitute whole body access. And conversely, we might have a very large opening, but no space to be inside beyond the perimeter, so that does not qualify as whole body access either. What we need is both. We need a perimeter that we have access to, as well as space inside of it for it to be considered whole body access. So to the criteria to help clarify these two conditions, unfortunately, is still being developed in the U.S. market and standardization, but there's other resources available. When we talk about physical access, there's a European standard that's available that helps with defining some of the shapes and sizes where people could physically fit through, not just unintentionally, but also intentional access, like in the example of somebody crawling through a small opening. And in terms of adequate space, currently, most of this guidance resides in machine-specific standards. There's guidance in some standards dictating the distance between a physical guard and the nearest obstruction, and other standards provide guidance for presence sensing devices in the nearest obstruction. These are often different measurements, partly because in the physical application, physical barriers, there's what I call the soft tissue compression. It's easier to squeeze through parts of your body, your thigh, or other parts of the body against a physical obstruction and a fence, whereas with presence sensing devices, you don't have that compression issue with the soft body parts. So when we think about whole body access, there's one of the most common approach is reset and restart. And so let's take a look real quick at those. In a typical restart procedure, and a simple application where there's no whole body access. This is just a sliding guard that's interlocked. The hazard cannot occur till the guard's closed. So in this example, the machine stopped. When we close the door, whether manually or automatically, nothing occurs automatically. A separate manual restart must occur before the hazard can continue. This is acceptable when there is not the risk of whole body access. Conversely, if we do have an application where whole body access exists, so here we have a man door that's interlocked, you can enter inside where the hazards are and be undetected inside the perimeter. We have additional measures that need to be taken. So here, we close the door, nothing happens automatically. We have first a manual actuation to reset the hazard, which simply arms the control circuit, and then a separate deliberate restart, which brings it to the run state. And this is where one of the primary differences between whole body access occurs. So I'm going to take this moment and ask a question to my co-presenter, Kenji. Kenji has the unique view that he's both a designer and an integrator and a user of equipment with his role at BridgeStone. So Kenji, what are some key things that you think people in these roles of designers, integrators, and users can take away from this section of our presentation?
For the user point of view, the last slide was the key takeaway. When we implement the whole body access, at the minimum, we need manual reset for safety systems, and then separate manual restart for machine motion. So that was the key takeaway for this section. Back to you, Chris.
Thanks, Kenji. So when we look at whole body access as a whole, we have to consider the concept of risk reduction as part of risk assessment. So in the new standard, it says that there's many measures that can be used to reduce risk, and which ones or combinations used are going to be based on a risk assessment. So we do our initial risk assessment, we identify some initial risk, and if we decide that we're going to reduce risk with perimeter measures, whether engineered controls or awareness barriers, we have to evaluate if whole body access is present. And if it is, we're iteratively going to apply a combination of measures until that residual risk, the risk out, is deemed acceptable. So this is where we get into the different measures that are presented in the standard, which we'll go through now one by one. These are presented in a hierarchical order, and so what that means is that the standard recommends which ones should be considered first versus which ones should be considered later through the process. So we start with control of hazardous energy, simplified as lockout tagout, but it's more than just lockout tagout. It's how do you control the hazardous energy that could result in an unexpected restart of equipment. So we know OSHA has guidance. That guidance is from 1981-82, from when some machines were much simpler. They were either running at full speed or they were completely stopped. But equipment and machinery have progressed just like technology. So there's an alternative standard, a consensus standard in the US, which is Z244, which was recently revised and is about to be reaffirmed, that lays out a more pragmatic solution which implements this risk assessment concept. So first thing we do is evaluate, is a hazardous energy control program present? Because it's necessary no matter what. If it's not, we need to create one, and it needs to account for all hazardous energy sources, not just electrical. It could be fluid power, pressure, thermal, radiation, any energy source that could create a hazard. So if it's not established, we develop one. Once it is developed, then we go to the next step, which is identifying which tasks require access to the hazardous area. This is essentially the beginning of the risk assessment, identifying tasks. And then for each of those tasks, we identify if energy is required. And the delineation here is the big part where it differs from OSHA. OSHA says that only maintenance and setup require lockout, and operation can rely on safeguarding. Well, as I mentioned before, machines have changed, and there are some maintenance and setup tasks that still require energy. So that's kind of one of the differences. But regardless of the task, if no energy is required, the easy, simple, reliable solution is to apply lockout and or tagout to the energy system, to the control system, so that we don't have to worry about restart. However, lots of machines do require some energization. So what this gives us is an alternate path based on risk assessment. Once we do the risk assessment, we apply a safeguarding solution using what is called alternative methods. We document the process, whether we're using safeguards or lockout. We do the necessary verification and validation, review as necessary, and then we have to do a subsequent risk assessment to determine if we've achieved acceptable risk. If we have not achieved acceptable risk, we have to consider if additional measures can be applied. And if they are, we apply those additional measures and continue through that loop again. But if they cannot, then we have to take a more drastic approach of considering modifying the task or maybe even modifying the process or the machinery itself, and then starting at a higher level through this process until at some point we determine that the residual risk is acceptable and we can proceed as planned. So lockout is always the preferred methodology, but we have to acknowledge that not every task works with lockout tagout, especially with newer machines where some level of energization is necessary. So Kenji, I'm going to ask you again, what would be a key takeaway here for anyone playing the role of a designer, an integrator, or a user when considering control of hazardous energy?
Great. I have a two-part answer for this. ANSI Z2441 permits the use of alternative methods, but OSHA has not officially accepted yet. However, the primary goal for everyone, including OSHA and industry, is to prevent injury in the workplace. Last year, even OSHA requested for information to industry about alternative methods and lotto. That's the first part. And second part is introducing alternative methods into traditionally lockout-only facility is not simple. Especially during the transition time, our user can get confused because some machine can have a new alternative method and others can have a traditional lockout. Back to you, Chris.
Thank you, Kenji. So the next approach then to reduce risk with whole body access when lockout is not going to be functional for whatever the reason is to prevent undetected presence of individuals in the undetected areas. So there's two approaches to this. The first one is the one that is often overlooked, but I think a simpler approach, at least in terms of cost and implementation at times, which is to use a physical obstruction to prevent somebody from standing somewhere where they cannot be detected. This can be done in a number of ways, one of which would be using sloping surfaces. So I simply incline the surface so somebody cannot stand there. The recommendation is to use a slope of about 60 degrees, but depending on the surface material, depending on if there's fluids or other elements in the environment, a sloped surface of 45 degrees may possibly be sufficient. The next approach is to use fixed elements that are going to force somebody's body into the detection zone or into the engineering control. In this example here at the bottom, we see there's just a simple mechanical lip that is placed between the front of the machine and the light curtain so that physically somebody can't squeeze into that small area. Essentially their body is always going to be obstructing the light curtain in this example. The same thing can apply with interlock doors. You make the area so small that you can't physically close the door behind you that achieves the same result. And kind of an offshoot of that is the use of awareness barriers or impeding devices, just anything that's physically going to stop someone from being somewhere where they would otherwise be undetected. So if we look at an example, this is the back of a press brake. We see the presence sensing device, the multi-beam device, which is used to initiate the stop. That's our primary safeguarding method for the hazards. And when a person enters, it initiates the stop. But immediately upon entering, there's the possibility that the machine could start up. So there's multiple ways, again, to address this. This is whole body access, where the person inside the perimeter and exposed to the hazard. One solution could be to put physical obstructions, in this example, a sloped material, so that when somebody penetrates the light curtain, they physically are forced into the sensing field, either that or they're outside of the perimeter entirely. If this can be accomplished, then there's no need for a reset device. The other option to prevent undetected presence then is the one that people often jump to, which is using other presence sensing devices to detect when somebody is inside the perimeter. Here we see example where we have a vertical light curtain is used to initiate the stop, and the horizontal device is used to detect presence inside the cell, inside the point of operation. Another is a large press where we have a light curtain initiating the stop, but because tasks require entry into the area and the area is so large, we see an area scanner in here that's preventing restart. Or here we have a combination of a light curtain and an area scanner at a typical load-unload cell of a robot. So these are all examples of where the secondary device, the complementary device, is simply preventing the restart. And because it's not used to initiate the stop, the safety distance that we would apply to the initial, the primary device, does not apply. And those will be addressed in later white papers and webinars associated with the series that we're putting on here today. So here we have the same example. We have the same press brake. We have the same initial protective measure of the multi-beam device initiating the stop. And if we introduce a second device, presence sensing device, in this example, it's a light curtain. It could be an area scanner or safety mat or some other presence sensing device. So here the beams, the multi-beams initiate the stop, and the horizontal device here is what's used to prevent the unexpected restart. So now they're inside the perimeter, but they're detected inside the perimeter. So when that's the case, the reset would not be required. So we talked about safety distance briefly. It's going to be addressed in much more detail later in other white papers and webinars. But essentially, when we talk about the safety distance, there's a formula. We won't get into the formula, but when we're talking about the device that initiates the stop, in this example, the multi-beam device, that safety distance does apply. When we're talking about the device that's simply preventing a restart and nothing else, that safety distance calculation does not apply. All it needs to do is make sure that the person is detected inside the perimeter. So again, Kenji, I'll ask you the question, what would be some key takeaways here for people to think about when addressing prevention of undetected access?
Okay, this is not easy part, but there is no one-size-fits-all solution to reduce risk from whole body access. Through a risk assessment, we need to get feedback from our actual machine users. If our engineering team, including myself, hit a roadblock, we contact subject matter expert. My case, I'm lucky. I can call Chris. Hey, Chris. But other case, SICK also has a rubber and plastic specialist, so I contact them for possible outside-of-the-box ideas. Back to you, Chris.
Thank you, Kenji. So the next option was the one that we started with. It's one of the most common ones. Not necessarily the most preferred, but it's the most common. It's using a manual safety-related reset. So manual actuation of a reset related specifically to the safety functions. So we have to start with a primer with some background. That reset and restart are two completely different things. Reset simply arms a system, whereas restart actually initiates the hazardous situation that we're trying to protect against. The indication, the colors used for the actuators when they're manually actuated are defined by standards. The reset should be blue, whether we're using American or international standards, whereas the start, there's different guidelines there depending on what standard you're applying. And the prerequisites are different. For a reset, the entire safety function has to be armed. All doors, interlock doors have to be shut. All presence sensing devices have to be clear of obstructions before a reset can be accepted, whereas a restart can only occur also when the safeguards are in place and functioning, but also when the control system's been reset. And then the actuation of the two, there's different types of reset. There's manual and automatic. Obviously, we're focusing on manual versus the restart is typically a manual actuation. And it's important to point out that neither one of these is presence sensing device initiation, which is a completely different topic that we just want to make sure that's clear that reset, restart, and PSDI are three completely different things with entirely different requirements on them. So when we talk about manual safety-related reset, so there's some general requirements that apply across the board. First is that they have to require intentional human action. It can only be performed after the safeguarded space is clear of all individuals and any other extraneous equipment that could be in the way, think like ladders and toolboxes and other things that might be brought into the hazard zone. And it requires training of individuals. It's one thing to put the device at a place where you can see the area, but you have to train people to look and confirm that the area is clear of those other people and extraneous equipment before they actuate the device. And then the safeguarded space, everything in the span of control that's about to be armed needs to be within clear view, clear line of sight from that reset device. And then lastly, the reset has to be outside of the safeguarded space, so you can't walk in and reset the system behind yourself. So these are all general requirements. So here's a large machine. We see a perimeter on all four sides of a multi-beam device. And here, typically the main reset is going to be at the operator station. So you walk up, you look in one direction, you can look, you have clear line of sight to the left, you can confirm nobody's there, you look to the right. And unfortunately, in this application, we do not have clear line of sight. There's an area where somebody could be back there. They might be tying their shoe, picking up a dropped tool, or simply doing a task that requires them to be in an area where we can't see them. So in this case, a single reset would not be sufficient. So options to address that would be detect a person in the undetected area with a presence sensing device. We could use other lower cost solutions. We could install mirrors that provide visual view from the reset location, or maybe even monitoring systems like cameras, depending on the application and the facility. But another solution, a simpler solution, might simply be to introduce another reset device, which would require somebody to walk over to a space where they do have clear view of that area. And then both of these resets would need to be actuated before the restart could occur. So there's options with multiple resets. One is that there's a very small space, and I might want to introduce resets just simply based on task. So in this example, I might want to walk out and go to the right to pick up one part. As long as that reset has clear view of the span of control, that's fine. I might also want to introduce another reset on the other side for the other 50% of the time when somebody exits the cell and goes to the left, just to save on steps and increase efficiency. As long as both of them have clear view of the span of control, it can be an either-or application. The other scenario with multiple devices is if there's limited view of the span of control. So in this example, main resets at the access door, but there's part of the cell that we just can't see. There's obstructions in the way and we can't see. So an alternative solution is to introduce additional resets, like we discussed before, that require some sequencing. It requires me to walk in, make sure nobody's behind the machine, walk out, close the door, initiate the final reset before the restart can occur. So all of them have to be actuated. And the final one, in this case, the one outside the main door, has to meet the requirements of the single device. So outside, not accessible from inside. And a risk assessment might determine what other elements need to be applied. It could be some time requirement between them. It could be sequencing. In this case, we'd actuate the one inside the cell before the one outside the cell. Location, position are all things that need to be considered. So again, Kenji, what would be key takeaways for our attendees to consider here?
Well, here, people tend to get lazy, including myself. And pushing a safety reset can become a habit while forgetting to check noise in that area. The combination of the operator's orientation in the work area and the location switch can improve the possibility of seeing that area. Back to you, Chris.
Thank you, Kenji. So the next thing we talk about, we kind of alluded to there before, which was locating the safety-related manual control devices. So what does that mean? Well, what is a safety-related manual control device? This is any type of actuator which requires a deliberate human action, and when actuated, could cause or result in harm to people. So think about push buttons, selector switches, foot pedals, anything that's manually actuated to do certain functions. It could be like reset. It could be starting or restarting the equipment. It could be unlocking an interlocked guard, a guard locking door. It could be something like jog or inch function with hold to run control. These are all safety-related manual control devices that, when actuated, could introduce risk or result in potential harm to people. So this is what we're talking about when we talk about SRMCDs, safety-related manual control devices. The caveat here is that the hold-to-run device would not qualify if it's already being used in conjunction with some other risk reduction measure like an enabling device. But essentially what we're saying is if you can actuate it and it could cause or begin a chain of reaction that could result in harm, you should not be able to access it from inside the safeguarded space. So it's not a new idea. It's been around forever. These are examples from international standards like the Machinery Directive. There's a requirement in there that control devices have to be outside the danger zone and positioned so that they cannot cause risk. And there's a B-type standard out there for integrated manufacturing systems that the reset actuator shall only be actuated from outside the safeguarded space. When we talk about control systems, we have requirements. When we talk about machine-specific applications like robots or presses, there's requirements out there. And what you see here is that the terminology and the phraseology is slightly different from case to case, but at its core, it's requiring the exact same thing. And what's great is that ANSI B11.19, this new edition just released in January, is the first standard that actually puts some criteria to that to help you evaluate and determine if you're meeting these requirements. So here are common examples. We saw this one already. We have a light curtain, we have a reset device, and if this person can reach over and access it, that's bad. Here we have a light curtain that's with the reset, but the light curtain's not right up against the fence, so somebody inside can reach between the two and reset the system. Here's another example, very similar, where the light curtains are separated from the mechanical fence. You could reach around the outside of the light curtain to the reset. This one's even more interesting. The light curtains there, they put the reset on a mobile pendant and just slung it over the fence so you don't even have to reach anywhere. It's right inside the safeguarded space. Here we have with an example of a horizontal detection with an area scanner. We have the reset and clearly the person can lean over. And actually here, that low fence makes it even easier for them because they can lean against that fence to reach into the reset. So all of these are examples of things that we should not allow. All of these go against this intent of locating the safety-related manual control device so that it can only be accessed from outside the safeguarded space. So as I mentioned, B11.19 now has guidance on this. We'll talk about this in much more detail in the next two webinars. The next webinar and white paper actually address barrier guards, and essentially the reach distance is based on ergonomic anthropometric data. We want to make sure that you can't reach something bad. Typically, we consider it to be the hazard zone, but if I'm inside, I can use that same information to tell me where to locate my SRMCD. The same applies with presence sensing devices, whether they're light curtains or presence sensing that you can reach over or you can reach through. If it's a horizontal device and you can reach over, all of this guidance now has been repurposed and represented in the standard to give guidance to help designers design equipment safely and for integrators or people doing inspections and validation to confirm that the safety system is functional and achieves the risk reduction that we want. So again, Kenji, what would be a key takeaway here for our listeners?
In the past, finding the location for manual reset was a guesswork, or maybe a good engineering practice. But with new B11.19, not anymore. We can use B11.19 Annex and determine the location. Back to you, Chris.
Thank you. So as we continue down this hierarchy of measures that can be applied, the next one is what's called an inhibit function. There's two types of it. There's proactive and there's reactive. One is you do before the incident occurs. The other is you're in the scenario, and now what do you do to minimize its impact? So when we talk about proactive inhibit functions, examples include providing every exposed individual with their own means of control, whether it's an enabling device or a hold or run control. It could be a keyed reset system, so the person who is permitted to reset it has control over when the reset happens. It could be trap key systems, which require some sequencing and other criteria to logically be in place before the final master key can go back to reset the system. Or it could be other personal control devices used at the entry point. An interlock blocking device is an example of that. So here we have the interlock door. There's a perimeter, so we can walk in and be undetected, but some of them allow for the device or for the actuator to be locked in a position that it would not actuate the control circuit. So here we have the actuator of the switch associated with the handle. The handle's locked in an open condition, and proactively I can lock the door behind me, lock it in the open condition, and I'm ensured that nobody's going to restart the system with me inside as long as my lock is on the door. Reactively, the solutions include latching devices like an e-stop that are strategically located inside the safeguarded space in non-observable locations, so where we don't have clear view from the entry point or the reset location. It could be using interlock devices that can be opened from inside the safeguarded space, which is another measure that we'll talk about here shortly. It could be using the reset function that we talked about with some time limits associated with it. It could be the sequential multiple resets that we discussed. And what's important to understand is with the reactive devices, because they don't stop the scenario from occurring, there's an additional requirement that these reactive devices have to be readily accessible wherever people are exposed. They always have to be functional during every mode of operation, and also that they have to be used in conjunction with an initiation warning system, which is another measure we'll get to here in a few moments. So with the inhibit function, again, the reset, an inhibit to the reset function, it has to be available at non-observable locations. When we put these inside the cell, the location aspect we just talked about does not apply. We want to make sure that the documented safe work procedures are on file and that people have been trained on how to follow those safe work procedures so they know what to do when and if a hazardous scenario occurs. So Kenji, what would be a good thing to point out here?
Here, putting a lock on the interlocked gate is an inhibit function, and it can achieve a safe condition. However, it is not a lockup. For lockup, we need to put a lock on an energy isolation device, such as an electrical disconnect. Back to you, Chris.
Thank you, Kenji. So as we continue to work our way down, one of the measures I just spoke about was interlock devices capable of internal opening. This is also known as an escape release function, typically built into the device, but the entire application has to consider this. So when we talk about interlock doors, we could have simple interlock doors that initiate a stop when the door is open, or we could have movable guards that have guard locking devices so the door is locked shut until a safe condition is met, and then a solenoid is released that allows the door to open. In both cases, if we're using this to address whole body access, we have to consider both, either interlock devices or guard locking devices. In both cases, they have to be easily opened from inside the safeguarded space with or without power available. Deliberate opening or unlocking, depending on the device, has to be easily done from inside and not require additional means like tools to do the unlocking. The opening means or the unlocking means has to be manually actuated. We have to be able to get to it easily and perform it manually. When we're talking about locking devices, that manual actuation has directly have direct mechanical principle applied to the locking mechanism. So it's not simply pushing a button and removing power to the solenoid. It's physically forcing the mechanical locking function to open, because again, it has to be functional with or without power available. Continuing on, if we open the door or if we unlock the door, it has to initiate an immediate stop command to the system. And whatever the means is, whether it's opening or unlocking, has to be only accessible from inside the safeguarded space. And lastly, both cases need to be used in conjunction with an initiation warning system, which again, we're going to talk about here soon. So Kenji, what would be a good thing here to highlight?
In here, egress was a requirement for RIA R1506 1999 edition, but it is no longer mandatory. Egress is still optional for any whole body access. Back to you, Chris.
Thank you. So then the last measure we'll talk about here is this initiation warning system, which I've alluded to a few times already. There's a number of applications where an initiation warning system would be a good idea, especially on larger machines, whether it's process length, or if there's obstructed view you can't see over, or if there's multiple floors where operators could be in various parts of the system and not be viewed. These are all applications where an initiation warning system could help further reduce risk. Again, this goes by different names depending on the industry or the standard you're looking at, but essentially it's the same concept. So when we talk about general requirements for a warning system, it has to include some time delay and have either an audible or a visual warning signal, or maybe even both, that occur before a change of state of the machine controls. When a stop command is initiated or an inhibit function is initiated, it shall immediately cancel the warning system sequence, and the warning signals used have to be recognizable. If they're flashing lights, they need to be distinguishable from other flashing lights in the area. If it's an audible alarm, we have to distinguish it from other audible alarms or sirens or bells in the area. But keep in mind, we don't want to make it so loud that in and of itself it creates new hazards like hearing loss. And just like the other elements lower on this list, there's training and documentation that's required so people know how to recognize the signals and what to do when they see or comprehend them. So there's two subtypes of warning systems, and the selection's based on a risk assessment. As we said before, the warning is to signify an impending change of state or condition of the machine. So with a pre-reset warning, this is a warning prior to resetting the safety-related part of the control system. It takes the machine from an off state to an enabled or armed state, but does not initiate the hazardous situation. Conversely, the pre-start warning, the warning before the start of the hazardous condition, takes the control system from an armed or enabled state to an actual on or run state. So this is actually signifying that the hazard is immediately going to begin. When we use the pre-start warning option, it still requires that there's a reset function that has to be present, whether it's manual reset we talked about before or the pre-reset warning shown on the left side of the screen here. So one thing that's similar to both pre-reset and pre-start is the warning period. The warning period has to be a sufficient amount of time so that the person can recognize, perceive, and respond to the warning. And that warning period has to be at least 2 seconds long. It could be longer depending on the application, the type of machine, the environment, a number of factors that go in there. And some machine-specific standards might require an even longer time. Again, that warning has to be distinctly different from other signals so people can comprehend them. And the warning signal, has to occur throughout the entire warning period. The permissive period, however, is unique. It's only applicable to the pre-start warning system. It's not permitted for a pre-reset system. With this, there's a limited time that allows a manual initiation of a hazardous condition. That period is limited and occurs after completion of the warning period. And now here, this has a maximum time of 4 seconds. Other shorter lengths or durations can be chosen based on the risk assessment. And if that permissive period is exceeded, we have to start the system over again. And initiation of a stop command is also going to cancel the permissive period. So it sounds kind of complicated. We have a timing diagram that may or may not help with the explanation of this. So here, this is an example of a pre-start warning system with a hold to run system. So I use some actuating means to initiate the pre-start warning, and that warning, whether audible or visible, occurs for a minimum of 2 seconds. At the completion of that 2-second period, the permissive period begins. And here again, this is a maximum of 4 seconds, and any time within that period, I can initiate the hazardous condition, which in this case is the hold to run control, which controls the hazardous situation. At the completion of that manual actuation, a new 4-second permissive period begins. And as long as I actuate the hazard control in that time frame of the permissive period, the hazard can occur. Now, after I exceed that 4 seconds, if I then try to initiate a hazard or the condition, whatever it might be, if I've exceeded the permissive period, the hazard's not allowed to occur. What's required now is to begin the sequence over again, reinitiate the pre-start warning, go through the minimum 2-second warning, and then start a new permissive period. And this continues on and on. What happens if during the permissive period, somebody actuates an immediate stop signal, like an e-stop, that immediately cancels out the warning system and it has to begin again. And likewise, if during the warning period, a stop signal is initiated, that too will cancel the warning system and require the sequence to start again from the beginning. So there's 4 different scenarios that we're looking at. One is that we have no warning and we don't have to worry about anything. No warning period, no permissive period. That's pretty self-evident. The next one is that we do a pre-reset only. In this case, a warning period is required, but permissive period is not permitted. The third option is that we do pre-restart, in which case both a warning period and a permissive period are required. And the fourth option is that we do both a pre-reset and a pre-restart. So we have to consider which warning and permissive periods are applied when. And in addition, we also have to differentiate between the warning signals so that people know, is this light flashing telling me that it's about to be reset, or is it more urgent that the hazard's about to begin? So these are important things to consider with warning systems. So Kenji, what would be a good thing to highlight here?
So previously, both initiation warning system, pre-reset warning and pre-restart warning were not discussed separately. In the new B11.19 provide requirements for both. Our challenge is consistently implementing warning system in our facility, but at the same time, we need to avoid confusion if the same warning sound is everywhere. Work environment can get noisy quickly with equipment alarm and warning sound. Through a risk assessment, we have to be careful to reduce noise in the workplace and implement effective warning system. Back to you, Chris.
Thank you, Kenji. So now we've laid out all the different measures that are available. Now we have to consider how and when to combine these to reduce risk. So again, we said before that selection is based on risk assessment, but in most cases, in almost every case, you're going to probably need more than one risk reduction measure to get to a level of acceptable or tolerable risk. That whole concept of tolerable or acceptable risk is outlined in other standards, including ANSI B11.0 and ISO 12100, so we won't get into that. But essentially, we need to know that you sometimes need belt and suspenders, and a lot of times it's based on risk. If we really simplify it, some people are easy to please with just one option. Sometimes the risk is so at a level that we need multiple options, and at the highest level of risk, we might need a plethora of measures to reduce the risk to satisfy whatever the need is. And the number of and selection of measures is again based on the level of risk. So here's an example that's not uncommon at all, where we see multiple measures applied. We start with the manual reset. We have the restart located at a safe distance. We have an interlock blocking device. The interlock's capable of being opened from inside, and there's an initiation warning system. Here we see multiple layers combined together to get to a level of residual risk that's acceptable for this application. So now we can start to summarize as we're coming close to the end. So what we have to consider first is evaluating the application. Do we even have whole body access? Well, here's an example. It's an automotive cell. There's multiple hazards with robots and conveyors and other elements inside there. And we have to identify, is there a perimeter? In this application, yes, we can see that there's a perimeter that's defined. And we need to determine if it's a safeguarded space or just a simple perimeter. Well, here we're using engineered controls with fixed fences, interlocked fences, and presence sensing devices, so we do have a safeguarded space. And the question of whole body access, well, yes, there's access points for material and people to enter, and clearly there's enough space inside to be inside the perimeter. So in this case, yes, we have whole body access as well. So we start to go through this hierarchy of measures that can be applied. The first one is lockout tagout, if we can do it with controlled hazardous energy. For some tasks like maintenance, we don't need power available. Locking out is a great solution. Other tasks like setup, teaching the robots, for instance, probably can't be done under lockout, so it may not be suitable for all tasks. We then go to the next option. The next option is prevent undetected presence. Doing that with physical barriers or physical elements in this solution is probably going to be pretty difficult given the size and orientation of the work cell. So the alternative would be to use presence sensing devices to detect when people are inside the perimeter. In this example, we can apply a number of area scanners or safety mats or what have you and cover most of the cell. But again, based on the complexity, we may not be able to address all of the undetected access inside the cell. Then we move on to the next solution. The next option is manual safety-related reset. We could consider a single reset at the access door, but remember we have to have clear visibility of the entire span of control. So in this case, that's not possible. So we might have to consider multiple resets with the sequencing and timing that we discussed earlier. Another option could be locating the safety-related manual control device at a location so it cannot be accessed from inside the safeguarded space. In this case, the final and primary reset has to be such that you can't close the door and reset the system on yourself intentionally. We can look at inhibit functions. Proactively, we could use an interlock blocking device at the access point so that the safety circuit cannot be rearmed with someone inside. We could look at reactive solutions, such as locating emergency stops in the areas where there is not visibility from the access point. We might consider interlock devices capable of internal opening, whether they're interlocked or guard locking. These are both options that can be applied at the access point. Or our last solution is the initiation warning system, either initiating a pre-reset or a pre-start, or both can be used in this application. And keep in mind, if we use a reactive inhibit function or any interlock capable of internal opening, the initiation warning system has to be used with it. So what we see is, after going through all these iterations, there's going to be some combination of measures that gets us to a point where hopefully we've achieved acceptable residual risk. So again, that's based on the risk assessment. We stepwise will start with an initial risk that's not acceptable. We apply multiple risk reduction measures and get to a level of residual risk that is acceptable or tolerable. So Kenji, again, what would be a good thing to highlight here?
ANSI B11.19 has a lot of really information, and it's a 250-page document. It's a big one. Being an engineer, I hate to read it from front to back. However, I strongly recommend not to search and read only one section. At least once, you should read the whole thing to get the intent of this document. Back to you, Chris.
Thank you, Kenji. So to highlight that point, one of the things that was discussed in the previous webinar in the series was the reorganization of the standard. This is a visual representation of it, but essentially the first 5 clauses are kind of the bread and butter stuff that applies throughout. When we get to clause 6, this is really safety 101. What is the general requirement for any risk reduction measure that's applied? And then starting with clause 7 to the end, the risk reduction measures are delineated through the 3-step method or the hierarchy of control, and each one has additional general requirements for that subset. And in some cases, there's even general requirements for the subsets. So for example, clause 9.11 addresses whole body access. Clause 9.11.1 are the general requirements for whole body access. So as Kenji said, you don't want to try to cherry pick and find just the thing on initiation warning systems. What you need to do is understand the context and how the document is written. So in that example, you would need to understand the general requirements for whole body access, the general requirements for control functions, and the general requirements for all risk reduction measures, in addition to the definitions and responsibilities and everything else that go into the document. So Kenji's right, it's a large document, it's a very resourceful document though, and understanding how it's put together and developed is really important. Which leads us to then, where do we find more information? From our side at SICK, we have a number of resources available to you. We have the SICK USA blog. You can find articles and topics there for discussion. We have a number of white papers, including the white paper series that this webinar is based on. We had 2 white papers at the beginning. This one, number 3, is on whole body access. There's another one on physical barriers. There's one about to be released on safety distances. So there's a number of resources available here. And then on-demand webinars. The first webinar is already out there and available. Today's webinar, as Lisa mentioned, is going to be posted as a recording to be watched later. And we have additional webinars planned as well. So that's information available from our side from SICK. But more importantly, where do you get the standard? As we mentioned, the standard is new. It has an approval date of October 2019. It was actually published and made available to the public in January of 2020, so just a few months ago. There's a number of places you can obtain it. It is a copyrighted document, so it does have to be purchased. And if you're wondering, there is a purchase price. The list price is $359. As Kenji mentioned, it's a really large document. It's a very valuable document. And if that cost seems high, just keep in mind what our counterparts across the pond have to do. They have to buy multiple standards to get the same type of information, roughly 20 plus standards to get the same type of guidance provided in ANSI B11.19. And that cost really, in terms of comparison, $360 isn't a whole lot to complain about considering the alternatives. So with that, we're getting very near to the end, but hopefully, Lisa, we do still have some time available for some questions, and we'll let you moderate us through that with the time we have remaining.
Awesome. Thank you, Chris and Kenji. Yeah, we'll go ahead and take some questions. It looks like we have time for maybe 2 of them, but any questions that we don't answer, I will share with Chris and Kenji, and they can respond back to you personally. Chris, the first question is, are there any requirements or best practices for determining the amount of time allowed between activating multiple reset switches used when no location has a complete view over the area?
That's a good question, and it's really hard to answer. It's essentially going to be based on a risk assessment. The idea is that when you're using sequencing with the resets and there are multiple areas, you want to give the operator enough time to hit the first one, make their way to the second one, and scan the area before they actuate it, and make their way sequentially to the last one. At the same time, you don't want to have so much time between them that somebody can hit all but the last reset, go grab a coffee or have a cigarette break, and somebody walk by and accidentally or intentionally, regardless, actuate the last reset when there's been enough time for somebody to enter into the hazard area or the safeguarded area and not be viewed. So it's kind of a balancing act. You want to consider practicality, but also make it so that you're achieving the end result, that you're ensuring that nobody entered an area that you just checked. So there's no hard and fast rule to it other than using the risk assessment process and just some general concepts. One of the things I would think about is the approach speed factor of 1.6 meters per second is a common speed used in industry of people approaching areas. You could probably do some calculation there, distance between devices at a given speed, and give some additional factor to view the area and probably work your way into a time delay. But those are all things I guess you would want to consider.
Great. And the next question is, Chris, in your position, do you find yourself helping to solve new applications for whole body access, like starting from scratch? Or are there more instances of companies needing to adjust their current space to allow for whole body access?
That's an interesting one. Can you repeat that for me one more time, Lisa?
Sure, yeah. In your position, do you find yourself helping to solve new applications for whole body access, like starting from scratch? Or are there more instances of companies needing to adjust their current space to allow for whole body access?
Yeah, so it's a bit of mix. In my position, the role that I play in the organization, we're dealing with both new OEMs and integrators designing new systems, but we're also dealing with a whole lot of existing solutions or machines out there in industry. As we know, in North America, in the US specifically, OSHA's requirements are that the end user is responsible for providing a safe workplace. So a lot of times there's a number of existing systems out there that have whole body access applications that people didn't think about. The example like we had at the beginning with the light curtain on the press, just because it's not a large cell, like a robot cell, people often overlook the fact that someone could stand between the existing the device and the hazard. And so it's addressing those things. So I guess the answer is it's a mix of both, right? That with new solutions or modified solutions that are going out there, it's something we want to be aware of. With existing solutions, it's one of those unseen or unthought of concerns that still need to be addressed. And thankfully, with the information in the new standard, we now have guidance and a process that can be applied to help walk through the methodology to get to a level of residual risk that's acceptable or tolerable.
Great. It looks like that's all we have time for today. But again, I'll have Chris reach out to all the questions that we haven't had time to answer. And we hope to see our listeners again soon. Please visit SICK.com to stay in the know on our upcoming webinars. And Chris had a great slide of showing where you can find more ANSI information. And have a great day. Thanks again.
Thank you, everyone.
Thank you.